Hi, good evening. 6 o'clock. So I'm going to start rolling here. I'm going to go ahead and share my screen, and we'll go through our PowerPoint here. Do my normal organization of my screen here. All right. So we are doing number systems this week. I'm going to this might lecture might take a little bit longer. I don't know. I can go through it fast. I can go through it slow. You guys did a lot of number systems on your homework, ones and zeros, converting to binary to decimal, stuff like that. Just for a quick check, how did you feel about the homework on a scale of 1 to 10? Was it kind of making sense to everybody? The different number systems? What do you think? Yeah, I got some. Okay, yeah. It's some ups and downs. All right. Well, I can if I'm going too fast tonight, let me know. But if it's really making sense to you, what I want to do. You don't know how to show the work for BCD. We'll do it in class. We'll do it right now. I want to show you on the controller. So I've got a program up. I'm not online, but I can show you on the how to navigate the radix and stuff like that. Okay. So, anyways, I take attendance because it's on D2L. Um, all the papers have been coming back and getting graded, homeworks and everything like that. And quite a few people are caught up. I got just a few outliers on some labs. So hopefully we're pretty caught up. Now we might start getting behind again. I don't know. We'll see. Schedule update. I don't know if this is going to change or not. I typically go on a vacation myself at the end of March, so I can do D2L lecture, that's fine. But in order to accommodate the lab, I've got two options. Number one is I've asked Jeff to sub for me for the lab on that Thursday. And it would almost be an open lab. And, usually students do a pretty good job of figuring out. They don't get everything done, but that's okay. Or I can do, I can front load it where we do two labs on the Tuesday and the Thursday, back-to-back labs to try and get them done. And then when I'm on break, I can lecture for some short lectures and quizzes and stuff like that. So I don't know which one we'll do, whether we'll front load the labs or whether I'll have Jeff covered and we'll keep our normal schedule. Just try to work ahead and stay ahead, and then I'll try and be sure as we approach the capstone that everybody's got time to get caught back and everything like that. But now that everybody's caught up, let's just try and stay caught up. I guess is the moral of the story. So as we start getting ready for the lab, you want to take a look at it ahead of time because when you get there, these are going to get pretty rough. All right. The panel view one, the lab went pretty good. Very few problems with that last panel view lab. You're just kind of working through it, showing all the functionality of the indicators, the buttons, gauges, alarms, stuff like that. So just on a scale of 1 to 10, how do you feel about your ability to navigate around the panel view a little bit to put in tags? Feeling pretty good about it, yeah? Getting around? All right, wonderful. Because we'll be using them from here on out. Yeah, because we're going to be using them. Basically, we're going to be using them for entering, start stops for push buttons. We can do that. But the really big thing we're going to be used is to enter numbers. Like 1,000 or 1,500 or whatever you want to enter. That's what we need to do. We need to start working with numbers 6,823. The HMI can generate that number for us. Okay, so that's what we're using for them now. So hopefully you understand how to use those numerics. So remember when you're doing this, and we're working in the future as we get going, you want to be sure that you're online, and then you want to run your RSlinks Enterprise while you're online so that you can create all your shortcuts and your pass through to your CPU, not somebody else. And then you want to be sure to apply and copy it over to runtime and then be okay. Does everybody on a scale of 1 to 10 feel like you understand that you should be online when you're setting all this up, right? And you should see your lab. You got to see your lab when you're doing it and when you add your Ethernet adapter. So hopefully we're going to get through this a lot quicker. I know it's fine. It's when we introduce it, it's kind of tough at first, but then you really get the hang of it, okay? And then when you're refreshing, you want to be sure that if your pass-through is all set up, then you can just go online and refresh your tags. And then you can go offline and program away, program and modify things. But the tag, even if you're programming a lot, the tag that you probably want is the numeric input, where we're grabbing a number 8,673 from the HMI. So if you've got that tag in your tags, when you refresh them, you probably don't need to keep going back online and off, and then back on and back off with the HMI in order to get those tags. So as you work through, you'll figure out the most efficient way. Okay. Hang on. Got a sneeze coming. Sorry. You can't see the tag. Well, no, we did that. What is the process for programming and accessing a second screen? Remember, you have to create the second screen. You have to add an item to that screen, and then you got to save the screen, and then they'll let you name it. So a lot of people were like creating the screen, and they wanted to have a go-to to that screen. They're like, I don't see the screen. You actually got to put something on there, and then save it, and bang, it's there. So everybody, how you feel about the go-tos on a scale of 1 to 10, that you got to actually put it on there, save it, and then it pops up, and you can do the go-to between the screens. And it's pretty popular to have more than one screen on an HMI, so you're going to want to have different screens and have a go-tos and stuff like that. Okay, yeah, I think so. So those are some of the basic functionalities. Bad scheduling. I got a little video there. I'm not going to. You can watch this video, but this is called bad scheduling. Is some of I buy and sell industrial automation equipment. It's my little hobby, and a lot of times I buy and sell controllers. And so whenever I get controllers, I bring them in and clean them all up, broom everything off them. And I like pulling up the programs that's on them. There's no I/O, but here's an example of somebody said that if you're careful with your tags, you could associate the HMI with manual entry. That is true. If you were where you go to tag and then you go to make the connection, and if it's called PB1 or whatever, when you get the first one, when you go to the next one and you want PB2, you can just copy that in there and make the connection. If you know the names of the tags and you're very careful, you certainly can do that. I agree. Anyways, here's the program I pulled off of a PLC the other day. And it's this was like a Slick 500 or something. And notice that there's a lot of subroutines right here. And if you go in these subroutines, you see that there's a lot of bits and inputs. If you go in the I/O configuration, you see that it's got I/O module. It's got a DeviceNet scanner module. So there's gonna, how DeviceNet is. It's gonna have some crazy I/O going on with DeviceNet with the address and everything like that. And then, but if you come here, you see that there's no run comments. There's no, there's nothing labeled. There's a ton of bits. None of the inputs have anything on them for what is going on. Here's a unconditional jump to a subroutine in here. Here's your SDN. Here's your DeviceNet. Zero labels. I mean, can you imagine trying to troubleshoot this thing? Here's ladder 50. Once again, all kinds of bits being addressed here, parallel series, a bunch of jump to subroutines. So jumping to subs within the subs. These ones are conditional jumping of subs. Ladder 62, here's your timers, when you're done bits. And it's just bizarro, how crazy this is. I don't know. There's a latch bit right there. I don't know what this is. Look at this. Latching all these bits on. If I come right here and I do a cross reference on this bit, by the way, okay, look at this. It's like in different subroutines. Like, you're not supposed to use this more than once, but you got this latch and unlatch being used in multiple different subroutines and everything like that. So it's crazy. Like, I couldn't imagine being a tech or a controls engineer or something, say, hey man, the press is down, go fix it. Something's wrong with the program. You'd never, ever be able to find out what the heck was going on here. And so as we move forward, I really encourage you to do a good job of mapping your I/O, keeping it organized, do a good job of run comments, do a good job of coming up with tags that make sense and and that are good descriptors of what is going on. Okay, so I always find that funny when I pull stuff down. Sometimes it's good, but a lot of times it's really garbage. I don't know why people do that. But anyways, bad scheduling. Number systems and codes is what we're talking about. We're going to start with the decimal system. And the decimal system, we all know. I don't know how much we need to go on it, but this is the ones place. We start with 0 and we go to 9. And then this is the tens place. Once again, we're going from 0 to 9, 0 to 9, 0 to 9. But basically what we're doing is this is 10 to the 0 power, and this is the 1 spot. This is 10 to the 1 power, so that's the 10 spot, 60s. This is the 100 spot, 10 squared. This is 10 to the 3rd power, 10 to the 4th power, 10 to the 5th power, 10 to the 6th power. We all know how the number systems work for decimal, okay? And I don't want you to get too confused when we get to the binary or octal or something like that, but just be aware that you don't have as many numbers to use. We have 0 through 9. Octal has 0 through 7. Binary has 0 through 2, all right? And binary, once again, is on or off, and it might be some indication here. It's +5 volts triggers the high, and 0 volts is the low. But you know, these thresholds could be 20 volts. I don't know, whatever your machine is, right? But somehow you have a digital circuit distinguishing between on or off, between voltage and not voltage, with some threshold there, right? But our 0 and 1 is what we have. And so what we have with our binary is our least significant to most significant. So this is 1 1 1 1 1 1 0 1. And so I think everybody does pretty good at these right here. So I wanted to convert this to decimal. This is the 1s, the 2, the 4, the 8s, the 16s. It would keep going. So right here I've got a 1, I've got a 4, I've got an 8, and I've got a 16. So I just add all these up right here. I get 29. That's what I'm coming up with right there, 29. What do I have on my screen right there? I got 29, all right? 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s. So that's your binary to decimal, all right? And I think I'm going to do another one here in a minute. So maybe I'll ask you that. But here's our decimal systems. Once again, decimal goes 0 to 9. When we run out of numbers, we start over at 0, but then we got to put a 1 in front of it. And then when we go 0 to 9 again, when we run out of numbers, we go to 0, and we advance the next number, and it would keep going like that. For octal, you only have 8, so you go 0 to 7. When you run out of numbers, you 2 at 0, and you put a 1 in front. Run out of numbers again at 7, you go 0, you put a 2. You could go run out of numbers again, put a 3, okay? Hexadecimal, got 16, so you go 0 to 9, and then F. But then you run out of numbers, so you put a 0, and you put a 1 there, and then this goes all the way to F again, becomes 2. All the way to F again becomes 3. Binary, 0, 1, ran out of numbers. Put a 0 there, put a 1. Put the 1 there, run out of numbers, 0. Put the 1 there, you got 1, 1, so it becomes 0, and then 1. So the decimal, you can see the 3rd, the 4th, and the 5th, they're the most significant, starting to move a lot faster than you would with a decimal, where you become 99, then you become 100. Or when you get 999, you become 1000, okay? So conversion problem right here, what I got? I got 1 0 1 1 1 0. All right, that's what I got right there. Let's see what this converts to. So I got, here's my 1, 2, 4, 8, 16, 32. I got a 2, a 4, an 8, and a 32. So 32 plus 8 plus 4 plus 2. I got 46. Is what that converts to. All right, 46. So did I do that here? I don't know if I showed you that. Okay, so that's pretty quick on binary to decimal. I think that people get that the best. So how do you feel about how binary counts and then the conversion here from binary to decimal. Can you do it? Can you do it on a quiz? Yeah, okay. And so I just want to show you, sometimes I do, this was what, 46? When I'm doing it on a PLC, I told you that I come up with a tag name and I call it masker or something, or math, or something like that. And what I do is I come in down here and I could make this 46 right here, and it's showing as in decimal. But if I wanted to see it as binary, I would click binary, and sure enough, it would be 10111110, which was what we had, 1011110. So if I really want to know it pretty fast, I'll just use the control logics to do the math real quick. But I know, I've done enough of this math that I can do it right here if I want to. All right. PLC memory is organized into bytes, single words, double words, bits. So we've already done the bits. We've done a lot of bits where this is 0 or 1, or 0 or 1, or 0 or 1. So we all hopefully feel pretty good about a bit. It's a single one of these that's 0 or 1. And then we've got a word, which would be 16 bits. A double word would be 32. Okay. And then we talk about, well, how much memory is that? Well, a byte is 8. So 2 bytes is a word. So 8 plus 8 is 16. All right. So if we had, you talk about memory of 1, I'm going to change this to like 1 kilobyte. So that's 8. A kilobyte is 8, and it can store 1,024 words. So a kilobyte is good for about 8,000 bits. A 1K word, or 16-bit word, is double that, because it's got 16 bits. And it wouldn't be called a kilobyte anymore, but it would be 16,000. And we're talking about kilobytes, and then you went to megabytes, and then you went to gigabytes, and then you went to terabytes we're at nowadays. So you can do the math yourself to figure out that, a terabyte is however many bits that there is. That's ones and zeros. And it's getting to be large. So you're going to take, 1 gigabyte, multiply it by 1,000 is a terabits. That's 1 terabits number of bits. So it's obvious that his computer's got more memory and got faster and could process ones and zeros and handle a lot more. Things got pretty crazy. But I remember my first computer had 4K of memory. So it could store, it was 4 kilobytes of memory. It could store 32,000 bits, ones and zeros, which is not very much. That doesn't get you very far these days, but it worked. Registers. So we had a bit, each binary number. Here's the bit. A byte is 8 bits. A word is going to be a 16-bit word, or it can be a double word. Remember, there's 64-bit access on some computers, but here is 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 16. So that's a register right there, called a register or a word. The greatest, the most significant bit is the one that's going to be farthest on the left, and the least significant bit is going to be the farthest on the right. It's the smallest. All right. So if I had 3495, let's say. This is my most significant, and that is my least significant. Okay, so yeah, okay, so that's where we're at on this. So how do we feel about this terminology here? We got it memorized: bits, bytes, words, double words. How are we doing? Scale of 1 to 10. You got that memorized? All right, hope so. Decimal to binary. All right, gets a little bit better here. People struggle with this a little bit, but just like I tell my kids, when you get the answer, go back and check it to be sure it's right. Okay. So what you're going to do is you take the number that you're converting and you divide it by 2. So 57 divided by 2 is 28, but we have the remainder of 1 because 28 times 2 is 56. So 57 divided by 2 is 28, remainder of 1. Take the 28 divided by 2. Well, that's clean. That's 14. but it's got the remainder 0. 14 divided by 2 is 7, remainder 0. 7 divided by 2 is 3, with a remainder 1. And finally, 3 divided by 2 is 1 with a remainder 1. And then you're going to read this way from the most significant to the least significant. So it'd be 111001. So 111001. That's how you convert decimal to binary. And I think I have, I think we do one right here. I got 47. Hang on, let me pull this up. I got 47 to binary. Let's see it. 47 divided by 2 is going to be half of 4 is 20. Half, we're going to get 23 out of there because that would be 46. And I would have remainder 1. So divided by 2. 47 divided by 2 is 23, remainder 1. 23 divided by 2 is going to be, I'm going to get 1 there, I'm going to get 1 there, it's going to be 11. But that's only 22, so I'm going to have remainder 1. 11 divided by 2 is going to be 5, but that's only 10, so I have remainder 1. Ooh, that's a lot of ones. 5 divided by 2 is 2 with remainder 1. And then 2 divided by 2 is 1 with remainder 0. So let's see if that works. If I work it up this way, it'd be 1, 0, 1, 1, 1, 1. That's what I get right there. But I said you should always check it. So this is, I got a 1, I got a 2, I got a 4, I got an 8. There's no 16, but I got a 32. So 32 plus 8 plus 4 plus 2 plus 1. I got, there's my, what I got here? Oh, 40, 44, 46, 47. So that's how you do that. So I always check it when I get done. Or if you just want to pound this out, you can do that as well. You know that it ends in an odd number. So whatever you get for your numbers here, you know you're going to have a 1 on that end. And then start working up the biggest numbers that you can. So 64 doesn't go into here. So that's the 1s, 2s, 4s, 8s, 16s, 32, 64. So that wouldn't be there. 32 goes into there, obviously. So you could say, oh, 32 goes in there. 32 minus 47 is 15. Okay, 15, what's next? I can put an 8 into 15. Okay, then I get a remainder of 7. And then I can get a 4 in there with a remainder of 3, you know, so it starts working up the same. And you can always kind of reverse engineer it like that, or you can do the divide like I do. But then you can always just go back and check it to see what it is. And you might be wrong. And if you're wrong by 2 or 4 or something like that, you know that you can just throw a 1 in there and then it'll add up. So that's a little more complicated going from decimal to binary, but here's showing right here is converting decimal to a binary. Here's 47 divided by 2. That's where they just kept dividing like I did, and then you work backwards. So talk to me about that scale of 1 to 10. You'll be able to figure out how to do that. And if you screw it up, at least check it and be sure that you don't turn in the wrong answer. Practice a little bit if you're not sure. The key is to check your answer, because if it's not right, I would not turn that in. Negative numbers. So we do have negative numbers, okay? And binary systems can not only use negative, but can use it to have positive, and it's going to have a polarity, okay? And a signed binary number, the leftmost bit, which you think would be the most significant, it's on the left. 0 indicates it's positive, and a 1 would indicate that it's negative. A signed bit is located in the most significant bit. So you could have, you know, this going on right here, but if you throw a 1 on it, you know, this, you know, you think, well, there's the 1. I got a 2 here. There's a 1 and a 2. That's 3. That's a 1, 2. I got a 4 here. But if you have a sign bit, the 1 makes all these numbers negative. So if you wonder how the negative is going, like if you have a negative counter value, you can go in there and you'll see that you'll have a 1 on the sign bit, which would be the most significant bit. All right. That's how signed binary numbers work to get positive and negatives, all right? Just be aware of that. Hexadecimal systems. So hexadecimal uses a base of 16. Now, the base of 16 is great because if you're using a 16-bit word, you know, where you have zeros and ones, it'd be nice to, you know, have a straightaway number that corresponds to that, okay? And so hexadecimal, unfortunately, you know, in our normal number system, we only have 9 numbers to work with. And so what we do is we start throwing letters after them, okay? So the hexadecimal version of 12 is C, hexadecimal. Hexadecimal C means 12, but hexadecimal 5 means 5. Hexadecimal E means 14. And how do these binaries work? Well, let's just pick one. No ones, no twos, no fours, but I got an 8. So that the equivalent there is binary is 8. So hopefully you understand the premise of hexadecimal, working with a 16-bit word. It kind of makes sense. Conversion activity 3, it's right here. The hex number is used in PLC because the word of data consists of 16 bits. So just like when we were doing decimals, we had the first slot here, which was the ones. Okay, so when we were doing decimals, let's say I had you know, 5638. This was the ones. This was times 10. That's the tens. This is times 10 times the hundreds. This is times 10 times the thousands. You know, the next one's 10,000s, 100,000s. Everything's times 10 because it's base 10. When we were doing decimal here, this was ones, then twos, then fours. Times 2 is 8, times 2 is 16. It's base 2 times 8. It was octal. It's ones, 8s, 64s, 564s, 528s. You know, 64 times 8 is 528. So like that. All right. So when we're doing 16s, this is the 1. This is times 16, which is 16s. This is 16 times 16, which is 256. 256 times 16 is 4,096. Each one of those rows goes up by 16 instead of 10, like we were with decimal. So we've got 7 ones. We got B, which is 11. So we've got 11 16s to the 1. And then we've got 1 256. So 256 plus 11 16s plus 7 gives us 439 as a decimal. So that's how you would convert hex. So what do I got here? Can I convert hex and decimal on this decimal? I got 439. Let's see if we can do it. So I come right here and I want to go to decimal. Let's see my fancy 439. There's my 439. And what am I doing to? Going to hex. I got 1B7 is what it says. My fancy calculator here says 1B7. And when I come back here, it says 1B7. So I just worked it backwards. I could, if you wanted to work it the other way, you just come here. Let's say I had 3B7. That's going to be a much bigger number, 3B7. And if I want to know what that was as a decimal, it's 951. But you could work it out, okay? So how you liking this? You feeling how to go back and forth between these on a hex scale of 1 to 10? Feeling all right about hex? Maybe even about using the PLC to figure out what your number is? All right, yeah, I think so. I hope so. Yeah, screw around with it. It'll help. And take a look at it. In the book, there's a good job of talking about it. Where we're at. Binary coded decimal. Now this is where some of the stuff that we're going to be doing with the lab today. Binary coded decimal, and it's pretty cool. It uses 4 bits to represent each decimal digit. Okay, so we use 4 BCDs for each decimal. So 0, it looks like binary, but it's not. And the decimal goes from 0 to 9. So our BCD goes from 000 all the way up to 1001 because there's a 1, no 2s, no 4s, there's an 8. Okay, so we got 8 plus 1 is 9. So we then just replicate this for our second number. So let's say I had, if this was 0001 and I put another 00001 in front of it, that must be 11. That would be 11. Let me look. There it is. This is a 1 and that is a 1 and it gives me 11. Just like if this is a 9 right here, 1001, if I put 10001 right there, I get, I would get 9, a 9 there, and then my other one would be a 9 there. So if I went like that, 1001, 1001, if it was binary coded decimal, not binary, it would say BCD here. This is 9 and this is 9, so it would come up as 99 base 10. If I had a 1001 here, it would be 999 base 10. Okay, so binary coded decimal, convert this. So we would want, let's see, do I show you? It's 1678. So I'm going 1678. And so here we go. I got 160001. Let's see, 6 is 10, oops. 6 is 0000110. So I got a 2 and a 4. 7 is 0111 and 8 is 1000. So there's my number right there. I just converted the 8 into this, the 7 into this, the 6 into this, and the 1 into that. And then I got to write BCD down here because it is not binary. It's binary coded decimal. It's different. And you'll notice if I come to my thing right here, I don't have the option of going to binary coded decimal. I cannot directly do that using my little cheat here on my program with my master. You got to figure that out, but I think it's hopefully pretty straightforward that you can figure that out, and that's what it's showing here. I got 7, which is, there's 1 plus 2 plus 4 is 7. 8 is, there's just the 8s. This is the 6 and there's the 3. So how do you feel about this? That makes sense? Converting this decimal to the binary coded decimal? Kind of select, right? All right. To distinguish between them, you have to have designation. You know, base 2 means binary versus BCD means binary coded decimal. It had a 10 here. That's just like a normal 49. That's base 10 that we work with. Or if it was 47 base 8, presuming there's binary coded octal, oh my gosh, I suppose you could come up with, it's not really there, but you know, if you wanted to come up with a number system to defeat the Russians in Ukraine, or you know, somehow mess up their computers, you go for it. But yeah, you could do something crazy if you want to, but it wouldn't exist that for anything that I know of. But you might be able to come up with octal. All right, but here's why by BCD is used. So back in the day, when you wanted a number into the PLC, you used a thumb wheel, and the thumb wheel clicked, you know, click, 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 and it would be an 8, a 7, a 6, a 5, and 4, 1, whatever, and it would read these in. So on my input module, if I click this to 1, I would have a light right here on input 1 because that would be reading that in as a signal that and then my PLC could process this with a BCD command. And then when I click this to 2, then this input would come on. The second input would come on and this one would go off. And then if I wanted a 3, you know, you have 1, 1. So this would be reading in your binary number, but then you would have a series of these, you know, you might have 4 of these because you would have 4 inputs tied up to this first one, 4 inputs for the next one, 4 for the next one, 4 for the next one. That's 16 inputs. That's what you have for a 16-bit IO card. and then you could bring in a number of 9999, and then get that converted to a decimal. Okay, and so that was the binary coded decimal entry, and we're going to do it. Now, here's the review of the thumb wheel. And so this BCD to segment second decoder, if you have this in some of a unit, a thumb wheel unit that's displaying it, this is burned into a chip in all the code that transfers your inputs into your display is burned into a chip. But what we've done on the PLC is the PLC's got an instruction for binary coded decimal that does all the math conversions and everything for you. And then when we push this out to our item right here, it's going to take our output card. Here's just showing the input. It's going to take our outputs and push them out to a thumb wheel display or a cathode display, and it's going to generate the number as follows. So over here, all the math occurs in here, by the way, all this conversion. If all these switches were open, all open right here, A, B, C, and D, well then what this segment, this decoder pushes out is 1 1 1 1 1 1 1 1 0. So it looks like A through F are ones. So this is on, 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 this is on. G is not on, but you can tell if all these are on, it's going to make a 0. And now if I go ahead and I click D shut right here, input, all the math occurs in here. This just push out a 0 1 1 and then all 0. So B and C come on. Well, B and C are 1, and it pops up on the cathode display as a 1. And you can see that as you go through these, so you want an 8, you would want, you know, all these items on. And so if you had a 1 0 0 0 1, oh, that's a 9. 1 0 0 1, we said, was a 9. And so it would do all the math here, and it would turn on all these except for E. E's right here. So you would have a 9. But we said that 1 0 0 0 1, you know it, 1 0 0 1, that's a 1 2 4 8. 8 plus 1 equals 9. So that math occurs in here. Turn these on to have it read 9. All right. So we're going to have thumb wheels where we're taking in data, and then we'll be pushing them out to this cathode display. All right. You don't see this very much anymore. Originally, when this lab was written, it was all with thumb wheels. I just kept it to do a little bit of math conversion, have a little bit of fun. But I've now mixed in the HMI where we can directly just bring the number in as a word or a double word. All right. And this is a lot cleaner. All right. Binary addition. What do we got, please? Yeeps. All right. Let's see if I can do it. Let me write it down. 0 1 0 1 plus 0 0 1 1. All right. You can add binary numbers. 0 1 0 1 plus 0 0 1 1. It's going to look like this, right? So how do I add it? 1 plus 1 is 2, but there's no 2 allowed. It's 0. We got to carry. 1 plus 1 is 2. There's no 2 allowed. There's no 2. 0. We got to carry 1. 1 plus 1 is 2, which is 0. We got to carry and 1. So I end up with 1 2 4 8. 8. Is that right? Well, let's think about this. This was a 1, a 2, or a 1 and a 4. So this was 5 plus, that's 1 and 2, 3. 5 plus 3 is 8. So it works. You can add. All right. Everybody, that seem reasonable to you what I just did? Yeah? Want me to do another one, or you guys got it? Everybody okay? Let me know if you want me to do another one. I'll do another one. Another. 5 plus 2 is 7. 5 plus, we all know that 5 plus 2 is 7. So let me just do 5 plus 2. So 5, by the way, is 0 1 0 1. 1. That's 5 plus 2, 0 0 1 0. That's 2. Okay. And so I added them. I just get 1 1 1. So this is 1. I got a 4 5 6 7 it just adds right away there. I didn't have to do any carrying or anything like that. So just remember, when you do regular math, if you get 9 plus 9 plus 2, there's no such thing. You run a number, so you get a 1, you got to carry the 1. It becomes 11. And that's all I did. That's all I was doing with all this carrying and stuff here. Mess around with it. And I think it's in the textbook as well for you to take a look at. Multiplication. 5 times 6. Yeeps. Let's do it. 5 times 6. I'm doing 5 times 6. 5 is 0, 1, 0, 1. And 6 is 0, 1, 1, 0. That's so we do 5 times 6. So I would go 0, 0, 0, 0 because I got the 0 there. Put a 0 here. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 0, 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 0, 1, 1, 1, 1. Ooh, is that right? So this is 1 plus 2 plus 4 plus 8 plus 16. That is going to be 20, 30. 5 times 6 is 30. So it works. Just like our math works. You just got to think about it a little bit, the way that you always have to carry if you have anything bigger than 9. In this case, if you have anything bigger than 1, you got to carry it. Okay? With a little practice multiplying it as well. Many PLCs allow you to change the format of the data so to monitor displays. That's where I was just showing you the radix, where you can go binary, octadecimal, hexadecimal, whatever. Okay, it's there, and I use it to cheat a little bit, but sometimes you want it to go. So I use the PLC as a conversion, and so if I want to have a PLC move to turn on outputs 1, 4, 7, 10, and 12. All right, 1, 4, 7, 10, and 12. So basically, you've got a word here, and if I wanted to output 1 on, what was it again? 1, 4, 7, and 1, 4, 7, 10, and 12. If this was my word that I wanted to turn on those outputs, this is 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. And then there's some zeros out here, but it doesn't really matter to me. Well, what I could do is I know that this is 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. Okay, so I convert it and I add all these numbers together. I get, I don't know what I get. I get about 2560. I got 2560 plus 64, 2624 plus 9. I get 2633. That's my decimal equivalent to this number right here is 2,633. All right. So if I had a program, let's say I'm going to make a little program right here. Let's make one down here. And I got to move this out of my way. If I put in a rung right here, and I put a instruction, and I said that instruction, where'd it go? I put something that's going to trigger this. And let's say I did a move, and I moved. My number was 2633, and my destination was going to be my output module. So do I have an output module here? It looks like I have a local 5 output right here. I just picked the entire module right there. I just picked the entire output module of the controller. Let's verify that I did that right. Let me come over here. 5 is a digital output. Yep. So if I hit this switch, it's going to move the number 2633 into the output module. Well, what does that mean? 2633 is represented by this binary number 0010 blah, 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 blah. So if that output module gets that, well, then this light's going to come on, 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 and this light's going to come on. And then those lights will be on 1, 4, 7, 10, and 12. All right. So as I explain this right here, that moving a number, a decimal number, into that destination will turn on the lights associated with the binary version of that number. I'll say it again. Moving a decimal number into an output module, not a specific one. I did not drill down here and pick data or anything like that. Actually, I should have picked data. I'm sorry. I should have. I got to pick data like that. I got to pick the whole module. That when I move this in here, I'd get a 1 here, a 4, 7, a 1, a 10. The ones would go there, and the lights would come on. How do you feel? Do you understand what I'm saying there on a scale of 1 to 10 of how that move works? Because we'll be doing it. You're going to be moving stuff. You're going to the output module here is a double word. So when you move ones and zeros into it, those outputs are going to come on, or it'll read inputs. And at my 26, it's 32 bits, right? So 2633. You know, I'm not even touching the bits on the other side. Remember, this only goes up to the 12th bit, I believe. But let me just check it. You don't trust my math on 2633. Let's go here. My masker was 2633, and that was going to be binary. So I had 1, 4, 7, 8, 9, 10, and 11, and 12. I got it right. Those were the lights that would be coming on. So if I activated this double word right here would get moved into this, that would get moved into there, okay? And so you could come here and you could, this move takes this value right away of 2633, okay? And then it'll move it and convert it to decimals there. Or you could do this. You could come right here. Oops, I was there anyways. Watch this, everybody. Watch what I'm doing, because it doesn't take binary here. This move is taking a decimal, all right? Or it could take, a tag, because we no longer have N7s in this. It'll take a tag. So I came right here and I called my local tags. My tag is masker. I could come right here. Sorry. I could come right here and I could pick masker. Okay. And then look what pops up, 2633, because that's what I had in here for my little cheat. And if for some reason I want, and it would do that, if for some reason I wanted, 46, 45, 32, I don't know, whatever that is, 45, 32. Well, that's part B. It's going to move 45, 32 into this output module. Well, what is 45, 32? I don't know. I mean, you could, here again, sorry, I keep going. It is all of this numbers right here is what 45, 32 is, okay? And so that's why being able to go back and forth between binary here and then giving you a number is important, because a lot of times what we're doing is we're using moves and we're moving a number into a device, and this was an output module. Later on, we're going to be moving a number into a variable frequency drive. And each one of these ones means something. This one means forward or reverse. This one means accelerate, decel. This one means 3 seconds. This one means, every single one means something. So whatever number you push into the variable frequency drive with a move is important. And so you're going to need to convert those numbers, or you're going to need to put them into a temporary holding location. Mine's called masker. And then you could move masker into there. So when we're doing sequences, stuff like that. So basically what we're going to be doing file and word manipulation, and that's why we're converting between the two. All right. So does everybody see a little bit here how it might be important to know what this number represents as binary? If we move it somewhere that wants the binary number, and that's what we're going to be doing. And in the case we're doing today, we'll be moving numbers around, and it's going to be the thumb wheels, the BCD and the BCD out is going to want to understand what those are. All right. Lab sign n bit might not work. So there's a system variable handout that we go through that you'll take a look at, and in the lab you're going to enter system variables. And we're going to have to trick these to work a little bit. Might need to put some one-shots in there. It says quiz and lab, but I'm going to talk to you a little bit more, all right, about the lab. So this I don't want. This I don't want. So what we're going to do is we're going to bring a number in to decimal, all right? And so what this is going to be the command that I was showing you that kind of does a lot of the math that was occurring kind of in here, that instead of burning it onto a chip, the PLC's got an instruction set that does that math for us. So it says BCD in, and that's local 4-1 data. So it's going to take the entire status of the input module. So if depending on what inputs you have in on, like 1011011011 whatever, and that's going to turn that into a BCD number, and then we got to store it somewhere. Okay, so that is what this command does. And once again, if it's coming in from the thumb wheel, let's say I bring a number in on BCD, and I'll do an easy one once again. If it brings in 1001 1001 from the BCD, and these are all zeros out here, what number is it bringing in? A 9 and 9. And if I looked at my input module, right here, here's my input module, 3 4 1 2 3 4 1 2 3 4. I would see this input light on, this input light on, this input light on, and this input light on. And so that's what the thumb wheel is going to do to your input module. It's going to turn on a variety of inputs. We're going to convert it to BCD with that instruction. And so 99 is going to get read in into your module. And you'll see that that's what the thumb wheel will be set to, is 99. And so it converts these inputs here, just like I was showing you here. This is the output version of it, but the input works, just the opposite. That it's going to take those in as a BCD number. It's going to put in storage, and it looks like then we're going to, when we get done with this, we're going to take, we're going to massage it and do some stuff with it and store it. And we get done with a new number, we're going to do a TOD, which is an out. This is taking it out, all right? And once again, it's going to take that value and it's going to push it out to the BCD out, which happens to be the entire output module. And so if it does something to it and you push out a number, and for some reason your module no longer looks like this, it looks like it's only got these ones, these ones highlighted here, right? Well, that would be 00010001. And so you're going to see that you're going to get a 1 1. You're going to get an 11 on the LED readout. Okay, in the computer, the PLC is doing this BCD conversion for you, because that's not part of a standard radix that you can come down here and look at. That's a conversion to that BCD. All right, so that is kind of an example of what we're doing with this lab when we're taking in this BCD in, and we got to put it somewhere. Is storage to a temp holding location? Where's that? On here. So that's right. So you cannot directly move some of this stuff. You're like, I just want to like take this thing, this BCD out. I just want to move that. No, it doesn't really like that. It would want you to take in this data that's been massaged, and it wants you to do a move to a location and store it. So there might be a lot of moving going on where you're taking data, you know, in. You might be taking this data into storage 1, and you might move it to storage 2, at which point storage 1 and storage 2 have the same number in them, okay? Because this is always bringing in that number into storage 1. And then you can maybe take this storage 2 and then later on, you know, multiply it and divide it and everything like that without messing up storage 1, depending on if, you know, you're removing. So there's going to be a lot of kind of temporary moving of this data. And this data right here, just to reiterate, is going to be, where's my BCD in right here? That's what it is right there. Notice this is 1, 0, 0, 1 is binary, is what's coming in. But if you went to decimal, it's a 9. But you know, you set you're going to set that thumb wheel for 9. It's going to pop up something similar to this, okay? And that works. That's 9. Great, it makes sense. But if you go like this, and I make this a 1, and I'm going to come over here, and I'm going to make this a 1. So I got 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. I'll do another one right here. I'll do 1. Well, this number right here in binary coded decimal is 999. It's 999. But if I went here and I looked at it as decimal, where do you go? Not right here, binary. If I go and look at this as decimal, it's not 999 because this is binary. It's not HCD or BCDs, binary coded decimal. That's why we need that instruction right there in order to take that 1001, 1001, 1001, and then turn it into that, okay? That's my BCD in. And so just to remember that if I'm looking at a number here is binary left to right, and if I click this, it just expands it so it's shown vertically. So here's the binary bit here is, there's the 1, that's that 1, 0, 1, 1, 0, 1, 1, 0, 1. If I come right here and I put a 1, it's going to pop up right there, okay? So one's just a way to show it horizontally and one's a way to show it vertically. Once we get into moving words, it's really important to be able to see words moving vertically, but you know, you can see data moving vertically or horizontally. All right, so that's how you're going to start navigating and feeling good about going through these tags and understanding the radix that we're looking at and understanding, is it better for me to work with a decimal number on this, or is it better for me to work with a binary number? All right, so real quickly then, I got the lab right here. And it's talks about moving and adding greater than. So we've done this, but that's just a little talk about it, just to be sure you understand. Move and compare. So you're going to create a quiz master and a contestant. So this first one that you're using, you're going to enter numbers using the HMI. So you really don't need to worry about any conversions or anything like that, because the HMI is smart. It's just going to take your number in 23 or 56 or 4791, and that's just the number that it is. You can you do not need to map HMI inputs because they're all part of the screen. But yeah, otherwise you'll want to be mapping any input that is a standalone, you like a push button or something, you'll probably want to map it, but you do not need to map when we're taking the BCD in necessarily, because it's not, when we're tagging the whole output module, whole input module, it's not exactly like that. We were not so worried about the ladder scan when we're trying to use a thumb wheel, I guess is the point. So here's a little quiz using the HMI. Number systems, that's where we're using the TOD and the moves and all this kind of stuff. And here's my status bits. And it's in there about what's going on with the status bit. I've got a handout if you're getting a zero light or overflow or something like that, okay? And then they ask some questions there. And then you're making a calculator, and here's where I changed it. We're gonna mix it up. Half of the calculator, you're gonna take two numbers. One of the numbers, I'm gonna have you do it with the HMI. Let's say you're gonna add 3 plus 2. One of the numbers will be from the HMI, and one of the numbers will be from the thumb wheel. And then you're gonna spit the answer out, and I want it spit out to the HMI, and I want it spit out to the thumb wheel. So if you go 3 plus 2, the HMI will be 5, and the thumb wheel will be 5. So that's what this is. You're going to do, you're going to be adding these push buttons to multiply and subtract, and then there's the numbers that you'll do. So it's going to be pretty involved. I would, once again, read through this and take a look at it. But as you start going through, it's this part B that's dealing with the thumb wheel and the LED display out, so you know how to use it. You already know how to use the HMI. And then this is where I'm just kind of tagging them together just for fun. All right, so that's kind of where we're at with it. All right, so that's really what I got for you. I know it seems like a lot. The labs have been long. My best thing is just to get you in the lab and kind of mess around and see how it works. I mean, I think we're doing pretty good now that everybody's caught up, but come prepared to crank this out, because it's going to hurt a little bit, I feel, and I want you to be ready for it by prepping up on the lab. All right. So with that said, what questions you guys got for me? Questions? Anything? If you don't have any questions, the quiz on the HMIs is open. You can go take it. And then I'll see you on Thursday. But if you want to stick around, I will answer. There's no pictures on the quiz, it's just multiple guess. I'm pretty sure. Trevor, you had the group homework, correct? It was, you had to consult the factor on order, and you gave me the path. That was correct. I think that's what it said, consult factory or something like that, or call. What else? I'm here for any questions if you want. You can just be sure people are getting on the quiz. That's always a good thing for me to do. People are on it, so it's available. Sorry, yep, no, it was whatever it said, call factor, consult, or something like that. Anything else? Otherwise, I'm done. You guys can go take the quiz.
I got a question, Sean.
Yep, what you got?
When you get the addresses in 5000 that read some word dot another word dot this word dot this word, you know what I mean? Compound addresses.
Okay.
I tried to set that up. You know what I'm talking about?
No, I don't think so. Say it again.
It might be a input dot slot to, like, spelled out dot
like local, yeah, like local
bit.
too, yeah.
not the actual local addressing, the base tag. I think it's an alias. I mean, I'm certain it's an alias, but I could never get it to work unless I'm using underscores. It kept showing up weird. I tried
You know,
doing that with my HMI bits. I made that dent tag and tried to use individual bits, but did I need to alias each individual bit of that dent?
yes. Yep.
Okay.
You'd have to alias each one. Yep. Whereas when you're programming your ladder logic, you could use that individual bit. But the HMI tag doesn't let you. It wants a tag, right? It wants an HMI tag, right?
Yeah, that's another thing is that when you what about creating HMI tags? Period. I've never experimented with that.
So that's what you were doing when you were pulling that tag list. So those were basically tagged to the HMI. So those were your HMI tags that were associated with the device back to there, and that's why you couldn't necessarily drill. It doesn't let you get into the word and everything like I was showing you guys to show you all the bits and everything like that. It just wants the HMI tag that's associated with it. You know what I mean?
Yeah, no, I wasn't creating that tag on the actual in the HMI
Right, but
software.
once you associate it with the HMI, that's what it is, and the HMI can't do that. It can't. An HMI tag can't really reach to the processor and pass through and get all the way into the bits and stuff.
All right, so if I had an alias for start and stop in the same two different bits in the same dent, then I couldn't do it that way.
You could, at that point, you created the HMI tag that it would, but it won't let you actually find that bit .0.1, right? But
Oh yeah, okay.
you could alias it.
Yeah, that's what I was seeing is that it would come up with the tag for the entire double integer,
Yep.
and I couldn't. Yeah, like you said, I couldn't dig down to the individual bit. So then I could just find that alias once I create the alias for that individual bit of that tag.
Yep. Then it will find the alias. Yep. Then you've got
Okay.
an then you've got an HMI tag. Yep.
All right. It seems to me that getting in that habit like that would increase your scan instead of creating 4,032 bit bools for each individual HMI bit. If you use this dent, it seems like that would make your program a lot shorter,
It just
quicker scan
depends.
time, and
It's still a tag, but that's another way to map IO. You can just map the whole word for the input module instead of mapping each bit. You just map the whole word, but you still need to go in then and then give the bit a description. Probably a good idea to give that bit a description, so that you know what it is, like PB1, PB2, PB3.
all right.
There's different ways to do it.
But then, as far as the tag names that that will have one word, like it might be sequencer dot level 2 dot step 5.
Okay.
I couldn't get that style of a tag name to work.
It should. If you alias for the HMI, if it's an alias and you can pass it all the way through back to the exact data that was created in the control logics program, it should be there.
Okay.
So we'll mess with it. You'll get better at it. But I wouldn't make it overly complicated. But yeah, you want to get a system that works for you. Everybody's got a little bit of a different system.
I just know when I'm troubleshooting something from the logic, I like to see certain exact pathways to certain information. Great, I'll see this alias for whatever input or output or however that might go. That's
Right.
great. I see that alias, but then sometimes I like to be able to see, am I getting the raw bit? Like if you're looking at a raw encoder value,
Right. No,
or
you're not
it's
getting
just
that. You
some
got to go
analog
to the
value.
map. You got to go to the map to see that, right?
Yeah,
Yep.
that's the kind of that's just how I like to troubleshoot.
Right.
Another thing,
Well,
I've come across a new VFD at work, and they got 1,000 of them on their scrap conveyor. that runs underneath all the press lines
Right.
that I work on as an Armor Start VFD.
Armor Star, yeah. I don't know what the exactly about it, but I think what's it hooked to?
Well, I mean, it's probably about 14 by 8 dimension wise. It's a pretty large package. Doesn't run very large motors. I think they're probably about 40 horse. No, not even 40 horse. Maybe like,
It's
I
a
would say 40.
it's a VFD, right?
Yep.
Yeah, no, it's a ABB, I think. It's Armor Star's, I think it's AB. Is
Well,
it Allen Bradley or is it ABB?
it's Alan Bradley.
Yeah. So Armor Starts they're out there. I think they're actually a little bit older. I don't know. They depends on what you're using them for.
Yeah, all this does is turn conveyor motors on and off, basically.
Well, I mean, it probably does some other things, but
Oh yeah, I just noticed there's 4 dedicated discrete input ports. You plug a micro cable straight into. There's 2 dedicated output ports like that. Trying to come up with an oiling system for. They've got all the steel hinged conveyor belts,
right,
and it's a stupid long process to oil them, and there's so much oil that gets wasted and just drips on the floor. I'm trying to come up with a more efficient and more
yeah,
automated way to do it, and all we essentially as maintenance guys have to do is make sure that the levels stay topped off.
right. No, you could put it on a timer or something.
Well, I have to actually develop the oiler. I'm going to have to run Ethernet, probably set up a point IO block now that I know how to do that. And
Well, well, the pen, and remember those Armor Starts are not Are they Ethernet device?
yes,
It is Ethernet. Okay, so you got Ethernet CPU. Yeah, you can do it. Yeah.
yeah, nearly everything in there is Ethernet.
All right. There you go.
And
Good. But it's going well. The new jobs are going well.
oh yeah, yeah.
Huh?
Everybody likes me, and they're uh, they're basically. I've come up with a couple ideas that I've thrown out, like that automatic oiler, and they're like, "Wow, why didn't we think of that?" I'm like,
Right.
I don't know,
Huh?
I did.
Yeah. All you need is
Oh,
you don't need
oh,
much, but
right. There was one more thing I was going to ask you about. Oh, if I want to make 2 PLCs that are on different networks running the same cell, what I mean is like the press
hmm.
is on like a 1050/50 network,
Okay.
and then that just sends out. I think there's some discrete input output communication traffic there, but
Oh,
I haven't investigated 100%. I know if we want to get online with the press, we have to be plugged into one network physically, Ethernet cable in a computer terminal cabinet.
right.
And then if we want to get to, because they run the coils, the coil steel or an aluminum,
Right. Yep.
a lot of jobs, and so it goes through a straightener and a couple other devices that manipulate it so that it's as flat as possible to begin with for stamping.
Right. Yep.
Those would be on like a 192, 168 network.
Right.
Now I know there's a way that I can make it so that we can just go get online from that PC terminal that stays. They have a computer at every press line that is dedicated to all communications for us to get on with PLCs and everything else.
Right.
And I'm just trying to figure out a way to network all of that. And can I do that through like a managed switch?
You'll
I
need
don't
a
know.
you'll need a managed switch. Yep. Exactly. And you just have to tell that switch that it can see that network. And then if for some reason a PLC on one of the networks wanted to use some IO or something on the other network, then you could generate a produce and consume tag if you wanted to. But it starts with a managed switch.
Okay, so then there is a way that you can send tag information directly from one network to the other through that switch.
Yep.
I thought I read something like that when we were like 2 labs ago. I thought I read something about that, but I never got a chance to ask or explore.
Right. You would need a managed switch, and then you'd have to do produce and consume tags if you wanted to use that data. But
All right, and then some of them, some of it is the Mitsubishi PLCs, and I don't think their tag system works the same.
Yeah, I don't know. I'd have to give that some thought of, yeah, yeah, I don't know.
I'd have to do some more homework on how to send tags right across. Because ultimately, what I really want to do is set up like a, not necessarily a SCADA, but at least like an HMI or kind of a monitor PLC system that'll send, like tank level information and faults and things like that. Maybe put in a data logger, something that we can monitor our little area that we're responsible for all together. It's all separate. You got to go to 8,000 different locations to check this and check that. And,
Right,
some of that stuff needs to be real time information.
right. No, you could do it with the problem is if you have two different PLCs, brands of PLC being read into like a panel view or something, then you've got to have a bus, and then it could get a little messy from there. But starts with a managed switch probably.
Okay. All right.
You good? You want to go take your quiz?
Yep.
All right.
Is this a draw it out and email it
Nope.
to you, Ken? Okay. I'll.
No. Mobile
All right,
guess.
cool.
Read
All right. Well,
carefully.
see you Thursday.
Yeah, it's going to be a rough one. We'll see you.
Is it?
Yeah, take a look at it.
All right. We'll do.
All right, bye.
Take care.